Okay, this is the second video for Thursday, April 11th, I think. And you don't need the combined gas law on this when you can use the ideal gas law because you have a pressure that's not changing. Recently, I saw a video that says a cubic meter in space has about 1 million molecules in it. I have not checked that, but you have the ability to do that. All you got to do is work PV equals nRT. It's similar to this problem. Find the moles and then use 6.022 times 10 to the 23rd and convert to particles. Molecules in the case of space, probably. So we're number 68, page 468. A physical chemist measured the lowest pressure achieved in the laboratory, which would be quite a bit less than space, although when it's that small, less is indetectable to a person. To instrumentation, yes. 1 times 10 to the minus 15th millimeters of mercury. How many molecules of gas are present in the liter sample, a liter sample, if the sample's temperature is 22? So very similar to this problem, the one I just posed. Well, your 22 has got to be converted to Kelvin, and then you have everything you need. Okay, you've got a liter, which is 1,000th of a cubic meter. Pressure of 1 times 10 to the minus 15th. You have to go to page 454, table 2, apparently, to get this one. 62.4 liters times millimeters mercury divided by moles times Kelvin. That's the same as degrees Celsius. It's just we should be calculating in Kelvin. And the temperature is 295 Kelvin by the time you convert. Because it's 22 Celsius, it's 295 Kelvin. Okay, so this table, no, you don't have to have it memorized. I'll provide you with that. Okay, so you've solved for this and you get 5.43 times 10 to the minus 20th moles, which is a little less than 1,000 or a little less than 1,000 particles. Because 6 times 10 to the minus 20 would be 1,000 times bigger than 6 times 10 to the minus 23rd. Okay, so when you multiply by 5.43 times 10 to the minus 20 times 6.022 times 10 to the 23rd, I forgot one was molecules, one was moles, so. You're going to come out to be 3.27 times 10 to the 4th, or 32,700 molecules at this pressure, which is quite a bit lower than space, although you wouldn't be able to tell the difference by pressure on a small surface. And that's 1,000th of a cubic meter. So I could believe about 1 million. Do the calculation, see what comes up. Moles cancels. Use all of your units. You're not using units, you won't have good numbers anyway. Next one, 73. Which of the gases in figure 15? You got a container of propane gas or a container of nitrogen gas. Occupies the greatest volume at STP. So you got to both be at STP. 0 Celsius, 273 Kelvin, 1 atmosphere. The masses are not the same. So you got to convert the masses to moles and then go from there. So I converted kilograms to grams. Kilograms canceled. 2 moles, grams cancels. 2 liters, and got the liter of propane is 265. In the kilograms of nitrogen, 2 grams, 2 moles, that's 28 because it's N2, not 14. 2 liters, and got 304 liters. Okay, since it is STP, the 22.4 liters per 1 mole is good for any gas. That's Avogadro. Okay, 70. 4. If the containers in figure 15 each hold 4 liters, what is the pressure inside of each? Okay, now you have to do a conversion. Okay, because the one that would occupy a higher volume at STP now has to be compressed down to 4 liters, more volume down to both 4 liters. So probably what I would do on this one when I turn the page is we got P1 V1 over T1 on both of these. Both of these at STP, converting to 4 liters. And we have to find the pressure. I was about to think, what is the pressure? Well, that's the variable. Okay, because the temperature doesn't say what the temperature is. Well, it does, because if you read, no, it doesn't. Assume ideal behavior. Okay, I haven't looked at this recently, but I think when I turn the page, I'm probably not going to put T2. I'm probably going to say the temperature doesn't change. Now, the interesting thing is, the combined gas law and Boyle's gas law, I think it's just those two, I'd have to fish through this, are affected by temperature. Because if you remember when we took the bicycle pump, if you squish the gases in a bicycle pump, you're going to do work. You would have added energy to that system. And so the temperature actually would not be the same on these. Now, if you just compress it once, it won't be a big difference, depending on how big the pressure and volume changes are. But if you do this repeatedly, or a big difference in volume, the temperature will not be the same. Since it doesn't say anything, we allow that heat to escape or something, and we're just using Boyle's law. Okay, I didn't do it that way, but it works. I chose to use the ideal gas law. I chose to change the 0.52 kilograms to grams to moles, and then put the moles PV equals nRT. I still use, though, wink wink, there's my 273 Kelvin, so when I put it in there, I didn't have my temperature going up. But it would in reality, some. And rather than use the combined gas law in the second one, I did the same thing. I converted kilograms to grams, grams to moles, and I used moles as N, and I put N here, it's 13.57. And my volume was 4 liters. I used 0.0821 on both of these because my volume was in liters, but my pressure is in atmospheres. And that's going to dictate that we use 0.0821 because the pressure is in atmospheres. And then the temperature is 273 Kelvin. And the propane comes out to be 66 atmospheres, and the nitrogen comes out to be a little more moles into the same space. It's going to be a little higher, 76 atmospheres. So you could use the combined gas law with this, surely, but ideal gas law is what I used. Okay, on to 84. Ammonia is formed by reacting nitrogen and hydrogen. This is called the Haber process or Haber process. We will talk about this extensively. How many liters can be formed from 13.7 of hydrogen at 93 and a pressure of 40 kilopascals? So we are using mass to moles to moles to mass, or volume to moles to volume, I think, in this case, because everything's a gas. And you have a reaction, and you have to do your moles to moles. So when you write the reaction, this is what you get. However, in real life, and the reason why we're going to talk about this extensively down the line is, this is not only a reversible reaction, the forward reaction is very unfavorable. You have to have tremendous pressures hundreds of atmospheres, and extremely high temperatures to drive this way. And even then your yield's only about 30%. You gotta keep recycling it. So that's beyond what we know at this point. We're just gonna say you mix some nitrogen and hydrogen and make ammonia. You don't, it's not that simple. Now, to balance the equation, we have 1 and 2. So you have to have 2 ammonias to get 2 times 1 is 2. That gives me 2 times 3 is 6 hydrogen. Here I have to have 3 times 2 is 6 hydrogen. If we know we have 13.7 liters of hydrogen, how many liters of ammonia do we have? So it's liters to moles to moles to liters. Okay. So let's say this is going to happen in a reaction vessel. It's going to be catalyzed and the conditions are the same. Well, they are the same during the reaction because it's equilibrium, and then they have to collect the NH3 off by compressing and cooling and get that out as a liquid and recycle. Tremendous amount of energy goes into this process of preparing this as fertilizer. Okay, but during the reaction, they are at the same conditions. And those conditions are 40 kilopascals, 93 Celsius, and 33.7 liters. Since the conditions are the same, it's 1 molecule, 3 molecules, 2 molecules, or 1 mole, 3 moles, 2 moles, or 1 liter, 3 liters, 2 liters, whenever the conditions are the same, which could be an STP or could be other conditions, but they are the same. So there's 13.7 liters, there's 2 liters of NH3, for every 3 liters of H2, H2 cancels, and you're going to divide 13.7 by 3 and then multiply by 2. And it comes out to be 9.13 liters. Last one, 90. Welding. Acetylene gas burns and produces water and carbon dioxide, and they give you a balanced equation there, which looks like this. And you've got mass to moles to moles to mass and volume to moles to moles to volume. It looks like on this one we're just going moles to moles. Okay, everything's a gas, so this is a G, this is a G, this is a G, this is a G. So we can go volume to volume as long as the conditions are the same. We have to have in order to balance this, if you did 1 and 1, you go back and forth, this would end up being 2.5. So we got to double everything. So 2, 5, 2, and 4 gives us 4 carbon on each side, 4 hydrogen on each side. There's 8 oxygen plus 2 is 10, so 5 times 2 is 10. So if you have a 10-liter tank at 25 Celsius in an atmosphere, how many moles of CO2? Well, you can take those gas conditions that are going to go in here and find acetylene. And then they're in a 2 to 5 to 2 to 2 to 2 to 4 ratio. Okay, but since you don't want to you could use combined gas law on this, P1V1 over T1 and P2V2 over T2. It would be awkward to do. They give you these gas conditions, just find moles. And then your moles are going to be the same. It'd probably be easier to stick it back into PV equals nRT again to find whatever you needed. Okay. So you put the acetylene gas in as an atmosphere, 10 liters, 298 Kelvin, and because this is atmospheres, that has to be atmospheres, which gives you the 0.0821. So when the table, make sure your pressure unit matches. Once you do that, and you multiply that out, N comes out to be 0.4087 moles of acetylene. Okay, and then earlier I said you just redo the PV equals nRT. In some problems you can do that. And this one, you are going to convert moles of acetylene to moles of carbon dioxide directly, and you're going to double these moles. And that's it for the review.